In the last module, we started with the Box-Jenkins model. We looked at the very simple purely random process, then we looked at the moving average process. We then moved on to the autoregressive process and looked at the autoregressive process of order 1 in great detail. What we will do today would be to look at the autoregressive process in general, that is a pth order autoregressive process. We have also defined the concept of stationarity and also looked at the function that the ACF or the autocorrelation function plays in the analysis of time series in the time domain. We will be looking at a couple of other functions like the partial autocorrelation function. We will also be looking at the concepts of causality and invertibility, and then we will look at a very special case of the AR2 process. Let us look at the autoregressive process of order p. The model for this is given by x t is equal to alpha 1 x t minus 1 plus alpha 2 x t minus 2 etc. up to alpha p x t minus p plus epsilon t, where epsilon t is white noise having 0 mean and a constant variance sigma square. Of course, the alpha j's are the parameters of the process. Let us rewrite this model by bringing in the regressors to the left hand side. So, we write x t minus alpha 1 x t minus 1 etc. up to minus alpha p x t minus p, and this we equate to the innovations epsilon t. Now, if we define b as a backward shift operator, which really means that b of x t is x t minus 1, b square of x t is x t minus 2 etc., then we can write this as 1 minus alpha 1 b minus etc. minus alpha p b to the power of p into x t equal to epsilon t. Or in short, we will define this as phi b into x t equal to epsilon t. So, we will write phi b or phi z as 1 minus alpha 1 z minus alpha 2 z square minus alpha p z to the power of p. We will call the phi function as the characteristic polynomial of the process. So, phi z is the characteristic polynomial of the process x t, and this plays a very important role, as we will see. Now, if you look at the stationarity condition, we claim that if the roots of phi z are all greater than unity in absolute value, then the ARP process is stationary. This can be proved. We can show that we equate phi z with 0, find the roots, all the p roots, and if the p roots are greater than 1 in absolute terms, then the ARP process is stationary. We will not show this for a general process, but we will look at this through the AR1 process, which we have already discussed in the last module. Remember that the AR1 process is x t is equal to alpha x t minus 1 plus epsilon t, and if you look at the phi z function in this case, this simply becomes 1 minus alpha z. Equate phi z with 0 and we have 1 minus alpha z is equal to 0, and therefore, the solution or the root of this equation is z equal to 1 minus alpha. And now, what the stationarity condition says? It says that the root must be greater than unity in absolute value. So, we have modulus of z greater than 1, which implies, and also is implied by, of course, that alpha has an absolute value which is less than 1. And remember that this is the condition for stationarity that we have already seen. So, for our AR1 process, we have seen that the parameter must be absolutely less than 1 for the process to be stationary. So, that actually translates to the fact that the root of the process should be greater than 1 in absolute value. So, this generalizes to a ARP model, although in terms of the parameters The ARP model becomes much more difficult to look at, but we will see what we can do later on. We will look at a very special case of the AR2 model later on. Now, when we have this condition that alpha is less than 1, let us look at when the stationarity holds in spite of this condition not being satisfied. So, let us look at AR1 process. X t is equal to alpha x t minus 1 plus epsilon t as before, and we say that alpha absolutely less than 1 means we have a stationary process. If alpha is equal to 1 in absolute value, then we have seen again in the last module that we get a random walk, and this is a non-stationary process. We saw that the variance depended on t. The variance comes out to be variance of x t is equal to t sigma square, and hence is dependent on t, so are the covariances, and hence the process is non-stationary. The question is, what about alpha greater than 1 in absolute value? Gamma h implies that it should be non-stationary. Why do we say that? Because we saw that gamma h came out to be sigma square into alpha to the power of h to alpha to the power of twice t minus 1 by alpha square minus 1, and it was a function of t, but that is simply because the way we have written it. Let us see how else we can do this. Now, let us rewrite the model as, so we take x t minus 1 now is the subject. So, we take this as the response, take alpha to the left hand side as well as epsilon to the left hand side. So, we have x t minus epsilon t equal to alpha x t minus 1, and then x t minus 1 is 1 by alpha x t minus epsilon t, and we will write this minus alpha inverse epsilon t as nu t. So, we have x t minus 1 is alpha inverse x t plus nu t. This is a very odd way of writing the model. We will come back to this. Here what we are doing is we are writing the past in terms of the present. So, we are writing t minus 1 in terms of t, but mathematically we can do this, and let us see what the consequences of writing it this way are. We will call this star, we will just name it as star, this equation. Then what happens is that if we keep on replacing the x t values, so x t minus 1 depends on x t, therefore x t depends on x t plus 1, x t plus 1 depends on x t plus 2 in the same way, and if we keep on doing this, we can write x t as summation j equal to 1 to infinity alpha to the power of minus j nu t plus j. Notice that it is not nu t minus j, it is t plus j, because we are looking at the future innovations now. But the innovations have an expectation of 0. So, expectation of x t is going to be 0. The variance of x t is sigma square by 1 minus alpha to the power of minus 2, provided of course that alpha to the power of minus 1 has modulus or absolute value less than 1. The covariance comes out to be sigma square alpha to the power of minus h divided by 1 minus alpha to the power of minus 2. Now, the first two moments are independent of t, and hence we can say that the process is stationary for alpha greater than 1 in absolute value. Is this a contradiction? Let us have a look at this. So, again just let me repeat this. We do the same thing as we did for the original AR process, only we now write x t minus 1 in terms of x t rather than x t in terms of x t minus 1. Repeat the same way as we actually did for the original process to write the x t value in terms of the innovations, but this time we have the future innovations that we can write the x t term in. And if you look at the innovations and if you look at the conditions, then as before, since now we have alpha greater than 1, which really means 1 minus 1 by alpha is less than 1, we can have a convergence, and therefore the variance would go to sigma square into 1 minus alpha to the power minus 2, which is independent of t, and similarly gamma h would be independent of t. In the present representation star, xt is explained in terms of the future values of the innovations. Now, this is a very unusual and unrealistic situation, particularly because what we are doing in the time series is that we have past data and maybe the present data, and our purpose is to model such that we can predict the future. And now what we have done is we are trying to predict the present or the past in terms of the future. So, the whole thing has got inverted, and therefore, this is unrealistic. And therefore, even if we have a stationarity condition, the second model is not tenable. It does not make any sense. Therefore, to distinguish between the two cases, we say that the ARP model is causal for alpha less than 1 with xt is equal to summation over j alpha to the power of j epsilon t minus j. Why do you say it is causal? Because it is caused by the past values. Xt, unlike in these model star where xt is caused by the future values, in the original model xt is caused by the past values, either of the epsilon. If you look at this representation here, then the infinite number of past values of the innovations, or by the past value of itself. So, it depends on xt minus 1, and this would be the more realistic model, although both models can be just mathematically shown to be stationary. So, when we talk about stationarity general for an ARP model, we will be talking about causality. So, causality means that it is stationarity given that the model is being explained by the past value. So, this is an important concept that we should be remembering. So, we should not be inverting the series mathematically to make it stationary, and if you do not invert the series, then we do not have a stationary process when alpha is greater than 1 in absolute value. Now, since we have talked about stationarity and causality, let us look at a slightly different but very close concept, which is the concept of invertibility. Now, invertibility is primarily associated with the moving average process. Look at a moving average of order 1, xt is equal to epsilon t plus beta epsilon t minus 1. We rewrite xt as 1 plus beta b epsilon t, which again beta is, b is the backward shift operator, or epsilon t is 1 plus beta b inverse xt, and we can write this in terms of the past values of the process itself, that is of xt itself. The innovation is expressed in terms of present and past values of xt. Now, if beta is greater than 1, the values of the remote past has more influence on current innovation than the recent past values, which does not really make sense, because the remote past would have less influence generally on current values than the recent past, and therefore, we want that beta is less than 1 in absolute value, which makes sense, because if beta is less than 1, the higher the power, the smaller would the values be, and hence the less would be the impact as we go back. So, this is basically the invertibility condition, which really says that the process is invertible if, in this case, if we write xt as epsilon t plus, it is a general MEQ process, beta 1 epsilon t minus 1 plus beta q epsilon t minus q, and then we write xt as psi b epsilon t, then the process is invertible if the roots of the characteristic polynomial of psi b are all greater than 1 in absolute value. Okay. So, in this case, it is a similar type of condition, again based on the characteristic polynomial associated with the MEQ process, and we have the same sort of condition, but in this case we are just inverting the AB process to write it in terms of the past values of the original process variable. Let us have a quick comparison between the MEQ and the ARP process, A MAQ process, as we have seen, is always stationary, but it is not always invertible. It is invertible if psi z has all roots greater than unity. Whereas for an ARP process, it is always invertible. We do not have a problem if we invert the process. In fact, it is very easy to do, but it is not stationary always. It is stationary or causal if phi z has all roots greater than unity. So, you see that the two conditions are, it is a sort of a dual condition for the MA and the ARP process. Now, let us look at a different tool for the AR process. Remember that the AR process, we showed this for the AR1, that the autocorrelation function becomes asymptotic to the h axis, but it never becomes 0, as we saw from the AR1. So, the problem is, how do you identify the order of the process? For a MA process, the autocorrelation function was 0 beyond q. So, once it becomes 0, you will be able to identify the order of the process, but in this case you cannot do so. So, what is done is, we take recourse to a slightly different concept, which is referred to as the partial autocorrelation function. The partial autocorrelation of order h, which we will denote by nu h, is the correlation between x t and x t plus h, eliminating the effect of the intermediate values of x t plus 1 to x t plus h minus 1. So, it is similar to what you do in partial correlations in regression. We eliminate the effect of the other variables, in this case the intermediate variables, and then calculate the autocorrelation. And the very nice thing that happens here is that if you do that, then the PSAF goes to 0 for the AR process. Let us look at a comparative study of the MA and AR process in these terms. So, for a MA process, the ACF becomes 0 beyond q, and this helps us to identify what the q value is like. For the AR process, the ACF becomes asymptotic to the h axis, but never coincides with it. Therefore, we cannot identify p from the SCF itself. On the other hand, for a MAQ process, the PSAF is asymptotic to the h axis, but never coincides with it. So, if you look at the PSAF, you cannot identify the order. For the ARP, however, the PSAF becomes 0 beyond p. So, it can be identified from the ARP, from the PSAF graph. So, what do? You have an ACF and a PSAF graph. From the ACF, you can identify a MA process and the order of the MA process. From the PSAF graph, you can identify the ARP process. So, whenever you look at a new process, you do not know what the underlying process is, you do both the ACF and the PSAF, and they help you understand what sort of a process we are looking at, whether it is a MA and then what the order of the MA is, or whether it is a AR and then what the order of the AR is. The other thing that we may look at when we look at a MA and a AR is that if you look at a MAQ process, x t is psi b epsilon t, and if we invert this, we have epsilon t is psi inverse b e into x t, and if we expand this, we can write this as x t minus delta 1 x t minus 1 minus delta 2 x t minus 2, etc. Or if you take the first term on the right hand side x t and you take all the remaining terms to the other side, you have x t is equal to delta 1 x t minus 1 plus delta 2 x t minus 2, etc. up to epsilon t, which means that we have a AR infinite process, a AR process with p equal to infinity. Similarly, if you look at an ARP, which is x t is equal to phi b epsilon t, and then if we invert this, it becomes phi b inverse epsilon t rather, and again you can write this as a infinite series. In that case also the MA process, this becomes the MA process of order infinity. So, both the MAQ process can be written as a AR infinity and the ARP process can be written as a MA infinity. We will come back and look at why we do not use one single process, because the other can be written in the similar way, and discuss the reasons for that after we do the ARMA processes. very quick at a very special case, p equal to 2, we have a AR2, and we have x t is equal to alpha 1 x t minus 1 plus alpha 2 x t minus 2 plus epsilon t, where epsilon t's are the white noise. The characteristic polynomial is phi z, which is 1 minus alpha 1 z minus alpha 2 z square. Now, let r 1 and r 2 be the roots of phi z equal to 0. So, that is the roots of the characteristic polynomial, and we know that for stationarity r 1 and r 2 must be greater than 1 in absolute value. That is fine, but what about stationarity in terms of alpha 1 and alpha 2? Let us see this. There are three cases that can happen. One is that r 1 and r 2 are real and unequal. The other is that r 1 and r 2 are real and equal, and finally, both can be complex, in which case one would be the conjugate of the other. So, let us look at this in terms of the parameters. Now, in terms of the parameters, you see r 1 and r 2 can be written as minus alpha plus minus square root of alpha 1 square plus 4 alpha 2 by twice alpha 2, and since the roots must be greater than 1, the modulus of this should be greater than 1. And after some simplification, this condition reduces to three things. One is that alpha 1 plus alpha 2 is less than 1, the other is that alpha 2 minus alpha 1 is less than 1, and the third condition is that alpha 2 lies between minus 1 and 1. Putting these three conditions, we have, if this is the alpha 1 axis, this is the alpha 2 axis, then these three conditions gives us a triangular region, and this triangular region, actually if we are within the triangle, then the stationarity condition is satisfied. So, if alpha 1 alpha 2 are such that the point lies, this coordinate lies within the triangle, you have a stationarity condition, otherwise not. The moral of this example is that it is much easier to look at the roots. If the roots are greater than 1, we know that it is going to be a stationary process. It is much more difficult to look at the parameters themselves. It was easy when we had a AR1, it is still manageable when we have a AR2, but from AR3 onwards these conditions become much more difficult, and hence instead of trying to judge stationarity from the parameters themselves, it is better to judge it from the roots. We will later on see how this translates to the ARMA models. In today's talk, we started with the ARP process, and while looking at the stationarity of the ARP process, we saw that there are conditions under which stationarity holds, but these conditions are not very viable because it depends on future observations. So, we have the concept of causality. As opposed to the causality and stationarity concepts in the AR process, we have a different concept for the moving average process, which is the invertibility condition. We discussed in detail what invertibility is. We also looked at another tool that we use in the analysis in time domain, because the ACF or the autocorrelation function does not work perfectly all the time. So, we looked at the partial autocorrelation function, and finally, we looked at what these conditions mean for a AR2 process. In subsequent lectures, we would be looking at the more general autoregressive moving average processes.